Good afternoon, everyone. We will be beginning now. Good afternoon, everyone who is present here, and thank you very much for taking time out of your day, especially this wonderful day that we have today. Weather, which is rare in the Netherlands. You're spending it here, cooped up with us. So we're very grateful for your time. So I would especially like to thank the teachers who are here to support their students and our sponsors who make all of this possible. Since the beginning, HARD has provided an environment for ambitious students who want to get more out of their time studying, to apply the knowledge they learned in class in a practical environment. Today, student challenges have been recognized as a vital part of education at a university level. And this year, we've taken on the challenge of designing our first electric vehicle to be more in line with sustainability goals of the world at large. To do this, we've committed to a 2-year plan to give us more time to get familiar with the unique engineering problem, which is building an electric vehicle. And so, after many long nights and many difficult challenges and many trials and tribulations overcome, today we'd like to present our progress at this rollout. And so, I'd like to also say that I'm incredibly proud of everything that this team has built this year. I'd like to say that despite everything that every member has sacrificed, all the time and effort put in doing so, we have built lifelong friendships, gained a tremendous amount of knowledge and skills that you'd find difficult to find anywhere else, and made something that we can really be proud of. And more than anything, I'd just like to say how proud I am of every single HARD member here today. You have taken time to build something, not for grades, not for credits, not for any kind of compensation, but out of passion. But so, I wouldn't want to drag on this speech too long. So, yeah, I'd like to say that today we'll be doing a quick recap of our progress that we made last year since last rollout in the 2024-2025 season. Then I'd like to talk about the team that we've assembled this year and what our plans are for competition. Along with, then I'll be passing it to our heads of our engineering departments for a quick summary of what we've done technically. We'll then have a quick summary of the progress made by the communications team at large, and just a quick note about our partners. So, last year, we competed in Formula Student Netherlands, where for the first time in HARD's history, we passed all of the mechanical and electrical scrutineering, along with a few of the dynamic tests. However, for the first time in recorded history, we had a failure of a Honda engine. This is an event still being studied by scientists today, as it's incredibly unique. And so we ended up coming in 3rd place overall in the combustion class event. And so this year, we've assembled a team of 46 students. That is up by about 20% from last year, from 16 different studies and 17 different nationalities. We have also supported one 30-credit minor project, one 30-credit thesis project, along with one student project, a relatively large study load relative to other years at HARD. So on the 24th of August, we'll be heading internationally for the first time since 2019. Nothing happened in 2019. And we'll be going to France to compete in the concept class event. The concept class event will give us an opportunity to present our plans and designs in a conceptual manner before we commit the time and resources to manufacturing in order to have a better chance of creating a fully viable electric vehicle. So now I'll pass the microphone to Sean, who will be talking a little bit about our engineering departments.
Yes, hello, I am Sean Martin. I am this year's Chief Engineer for the Hanze Racing Division. And as Greg said, I would like to go ahead and introduce our engineering departments. We have 3 of them, starting with our mechanical engineering departments. These people are responsible for kind of the skeleton and the dynamic structure of the car. Many of the projects that they'd be involved in are stuff like the aerodynamics and the bodywork, as well as creating the chassis, the drivetrain, pedal box, steering, and suspension. These are essentially the core components that help us harness the engine and allow us to run. Secondly, the jazz is too jazzy. Secondly is the electrical engineering department. These people are responsible for the brains that will power the car, stuff like the accumulator container, that is the high voltage battery that essentially runs the vehicle, as well as the dashboard, so we can relay all that information to the driver. And then things like the high and low voltage systems. Again, high voltage, the accumulator, but we have all these smaller subsystems that need to be run. And then finally the wire harness, which you can think of kind of like the neural system of everything. And then from there, we also have the driverless. These people are responsible for creating software to essentially give the car some autonomy and allow it to run itself. They use a combination of LiDAR, computer vision, and processing in order to effectively have the car drive itself through a series of cones, as can be seen here, through a set track. We'd also like to do a nice little shout out to our HARD alumni. They are not technically an engineering association, however, they are an amazing source of technical knowledge that we rely on every single year. They help us with many frequent events when it comes to, win the previous cars and having little projects about those, but also when it comes to their efforts at our engineering design presentations, where people over the year can essentially show them what we've worked on. They can give us their feedback as they are currently working in engineering disciplines that are useful to motorsport as a whole. I'd also like to give a little progress and roadmap. So our car will be built over the next 2 years. During this first year, we kind of laid down the foundation and groundwork design-wise, while next year we're going to be putting more of a focus on manufacturing as a whole. So starting with that, finishing up in June, we would like to have the primary component designs completely done. That is kind of stuff like chassis, maybe some accumulator design. And then going to August, of course, as mentioned, we are going to be participating in Formula Student France, and we would like to use that information at September, once we come back, to kind of update our designs based on the feedback that they give us from scrutineering. Going over October through February, that's when we will build the actual chassis and also other components. I have chassis and accumulator here, but there's things like the pedals, there's things like the steering system, there's plenty of electrical systems that we will like to develop during that time. And then from March to May, we would like to finalize those developments and then move into kind of a testing phase, where we can therefore roll out, again, the physical car, the HARD07, sometime between May and June of next year. Going from that, I would now like to introduce our lead mechanical engineer, so we can talk about the car's mechanical design.
All right, well, hello everyone. I'm Cooper. I'm the lead mechanical engineer, and we have a team of around 12 mechanical engineers currently within the team. They are subdivided right now across 9 projects, and they have been doing some great work, and I'm going to show you guys some of what they've done. So to begin, we're going to go over some of the systems. The first one will be the accumulator. This has been designed by Sem. Specifically, when I'm going over the accumulator, I'm only going to be talking about the container itself, none of the electrical components, because our lead electrical will be going over the majority of that. So to begin, the accumulator container is going to house all of the battery cells that power the car. This component is extremely volatile, so there's a lot of regulations within the rules about how this needs to be designed. So we have chosen to design this using manufacture this using aluminum and welding this together. And the brackets are going to be steel and placed inside the car. These brackets, by the regulations, need to withstand 40 Gs of acceleration in all directions. So this is a very difficult design to get and, of course, mount to the chassis. And the accumulator also needs to be removable from the car at all times. This poses a challenge because it is relatively large. It's around 400 millimeters by 600 millimeters. So it's large, and the chassis needs to be able to accommodate it coming in and out at competition because the accumulator has to go to and from scrutineering constantly. Next up, I'll be going over the chassis. This was designed by Krishna and myself. The chassis is an incredibly critical component. This is the frame of the car. This is what holds every subsystem within the car, and it needs to adequately fit everything with the space required, and while also being the lightest possible, because more weight decreases the performance. Many teams go for carbon monocoques. HARD has never done a carbon monocoque, and this year we will not be either. Carbon monocoques take a lot of time and resources to design, and unfortunately we just do not have those resources. So instead we're going to be continuing again with a space frame, which is proven. And of course the chassis is a very iterative design process because as each subsystem changes within the car, the chassis has to adapt to those changes. So currently the iteration that I'm about to show you is iteration 35. This has been iterated on since October, and currently this is where we sit. We're going to be using steel, and of course this is designed around all of the subsystems. We will be making a jig out of MDF that we then place the tubes into, tack weld, and then send off to our sponsor for professional welding, because as a Formula student team, professionally welding a race car chassis is not within our skill set. Of course, here's where some of the systems will sit. As you can see, the accumulator will sit in the rear, and that is why there's a large hole in the floor there, because the accumulator will be coming out of the bottom of the car. Now, moving on to uprights, or otherwise known as knuckles. These were designed by Job and Ramon. These are the foundation of the wheel assembly: your axles, your brakes, your tie rods, your A-arms, all of the suspension components, the steering components and whatnot, they all mount to this, and thus this goes through a lot of forces because this is your main point of contact between the wheel and your suspension. So all of the forces that come through there need to be able to be withstood by this component. So as you can see in the top right, we've done a good bit of FEM, and currently that is the front upright there, and it is going to be manufactured from 7 series aluminum on a 5-axis CNC. Now here you can see fully assembled uprights. The one on this side here is once again the front, and you can see the A-arms and where the brakes will mount, and here you can see how tightly packaged it is in the rear. There's about 7 millimeters of space in between the brake caliper and the wheel itself. And the rules allow for 5 millimeters. So of course it will be very tight, but because we are using CNC parts, we should be able to be within that range. Moving on to suspension, this was designed by Dimitar, Mikhail, Alexei, and Ramon. Suspension connects the chassis and the upright assembly. This is going to be directly actuated. Some teams go for push and pull rods, where you use rocker arms and actuate the suspension that way in order to get the best performance out of your car with the best ride and the best grip. We will be using directly actuated. That means that, as you can see here, this system will mount directly to the chassis and directly actuate the A-arms, keeping them on the ground. This is a simple system and also relatively easier to design and package within the chassis because we are doing an electric vehicle and we have an inboard motor. We're very constrained with size, so trying to keep every component that we can outside of the car is basically one of our goals. Our coilovers will be made by one of our sponsors, D3. He's working very closely with us to design a suspension system that will get the best performance out of our car. As you can see here, here is where it will roughly mount to the chassis in the front. And here is, once again, the system with the upright. Moving on to steering, this is currently in design, being done by Patrick, Nikiforos, and myself. We will be using a direct acting rack and pinion system. This here is the steering rack. We will directly actuate tie rods. If some of you are familiar, some teams will use a trapezoidal steering system where you have rockers again, but due to space, we will not be using that, and it is also simpler to design a system like this and more cost effective. In pair with this, we will be using a quick release steering wheel. This is necessary because one of the challenges at Formula Student is having the driver get out of the car in under 5 seconds. So having a steering wheel that releases quickly and efficiently is very important for meeting this goal. We will be making that steering wheel from just water-cut aluminum with 3D printed grips that are wrapped in a tape. And we will also be custom manufacturing tie rods, which are the lengths from the rack itself to our uprights assemblies that we just discussed. Moving on to pedal box. This was designed by Cameron and Jorn. This is the main point, one of the main points of input between the driver and the car. This consists of an accelerator pedal and a brake pedal. Our brake system is made up of 2 independent circuits. This basically means that if one fails, so say the rear fails, then the front system will still work, so our car will still be able to safely stop. And our front pedal, our accelerator pedal as well, all of it will be designed and manufactured using mainly water-cut materials with some purchased components, of course, such as the master cylinders and the brake lines. This is, of course, a full render of the system. You can see here, these rails will be welded to the chassis, and then there will be bolts that are passed through those holes that allow adjustment of the pedal box forward and back depending on driver height and preference. Moving on to drivetrain, this was designed by Ramon, and this component transfers torque from the motor to the wheels via a chain and sprocket drive. We use an MRAX 228 motor. We have estimated a theoretical top speed of 157 kilometers an hour in purely optimal conditions, so of course it will be a little bit slower than that. But yeah, and with this component, we've done a lot of iterations as well. On the left, you can see what was the first rough iteration, somewhat similar to what we have now, where we would tension the motor by sliding it and tensioning the chain that way. It also featured a single inboard brake because at that point in time we did not have a differential, which the differential allows your wheels to move independently on either side of the axle, which basically improves your turning radius. So as you can see in this design, that little silver part with the sprocket on it, that is now our differential that we have. And for this design here, our idea was to make this mount to the rear of the car, and this would then allow us to easily remove the accumulator from the rear of the car, retaining the torsional rigidity of the chassis and thus retaining performance. Unfortunately, it was realized that this was not rules compliant, so this idea had to be scrapped and we had to go back to the drawing board, which is how we ended up here with this design and this chain tensioning solution here. We're going to be using 6 series aluminum with a 3-axis CNC machine. Our 14:43 gear ratio will give us good power output at the wheels that will allow us to perform well at competition. Moving on to firewall, this was designed by Chris. This separates the driver from dangerous components and fluids. It's pretty self-explanatory. It's going to be 2 sheets of aluminum that are 0.8 millimeters thick, sandwiching a Nomex layer of fire retardant material. This will then protect our driver from any dangerous components within the chassis. It will be attached to the chassis using some simple brackets. And yeah, we're gonna move on to driver's seat. This is another component that I designed, and as a racer myself, I understand the importance of being secure in the seat. Because when I'm moving around in the seat, I find it very difficult to focus and it can cost me time on track. So designing a proper seat that really restrains your driver is very important. That is why we went with this aluminum design. While it doesn't look like it would just restrain your driver very well, when it's paired with a 6-point harness and a expanding seat foam that is molded to your driver that you can swap out very quickly at competition, it begins to hold your driver very securely to the point where they do not move around in any way that they should not. The 6-point harness will be used with a Hanze device. The use of a Hanze device greatly improves the safety. It is they are homologated in pretty much every single FAA automotive championship that's current today. They reduce neck tension in high impact collisions and have saved many lives. So we're going to be going with that option because it is extremely safe, even though it's not required. Doing that also allows us to use slightly smaller shoulder harnesses, allowing our driver's arms to be able to move slightly more. These will be mounted using steel brackets that are threaded and just bolts that drop right through the bottom of the seat, securing it in place. Moving on, I would like to show you how all of these components will come together into a final assembly. As you can see here, we have all of our components all together. We have our drivetrain there in the back, and the chassis with the seat and firewall and the accumulator container sitting right in the back there. And this nose cone was designed from carbon fiber and will of course be adapted on because it has not been fully optimized yet. So we're going to be doing some work with that. And next for the mechanical team is to close our design phase. So we need to have a completed design very shortly. We will probably have this done within the next 2 months or so that we can take full designs to France. Then once we go to France and we get our feedback, we're going to implement whatever changes we deem necessary. And then we can begin ordering our parts and our raw materials and begin manufacturing. And once we have all of our components manufactured and all of our parts, we can begin assembling the car. And once we have an assembled car, it's probably not going to work. So it's going to be a lot of iteration and getting everything to work. And then once we finally have a driving car, we can begin testing it and breaking things and testing again. I will now pass you off to our lead electrical for the electrical presentation. Thank you, guys.
Hello, everyone. My name is Ostap. I'm the head of the electrical engineering department at Hanze Racing Division, and today I'm going to talk about how the electronics come into the world of our car. I'm going to discuss mainly the overall the systems of the car. Then we're going to move on to the projects that we already finished the design phase of, and I want to talk a little bit about the educational aspect of working at Hanze Racing Division, and then I'm going to talk a bit about what's coming next after the rollout. So to start with the overview of electrical systems in the car, there's a small render of the car itself, and there's the cross-sectional view. All of the systems can be visible on this slide, where starting from left to right, we have the APPS circuit that I'm going to talk about later. Dashboard is the main point of exchange of information from the electronics of the car with the drivers. And then T-cell is also one more rules compliancy thing that we can just not go off without. Low voltage box houses main points of low voltage circuit of the car. Inverter is the motor controller. Then we have the motor, and the T-sack, which Cooper already talked about, is the accumulator container where we have all of the batteries. So to start off with drivetrain, how it's all arranged, we use a quite big battery. It's a 600-volt system. It uses 144 S5P configuration with the total count of cells is 720. Our total capacity is around 8.5 kilowatt hours, and estimated power output for peak is 105 kilowatts. Of course, we are going to limit this number to 80 as per rules compliancy. that's the main reason. But of course, we are also limited by mechanical grip of the car. So to be fair, we will never be able to unleash the full potential of the motor. But I guess that's better. That's the safety margin. So for battery management system, also known as BMS, we use the Orion V2. That is a ready-made solution that we just have to integrate into the systems. It ensures that all of these cells are at the same voltage, at the same power output and temperature, which is also assisted by the thermistor expansion module, which we have 2 of those, basically to monitor all of the temperatures inside of the battery container. Here you can see the top-down view of the TSAC itself. On the left side, there are visible cells, that basically the batteries, and on the right side, there are a couple of elements from governing electronics, which is the BMS itself and relays and whatnot. Moving on to the drivetrain components itself, it is our inverter, the DTI 550 LC, and MREX, the motor. Both of those were kindly sponsored by Hanze, which we are thankful for. And all of those things are water cooled, so we will have to design a cooling solution that is capable of dissipating heat efficiently. Here is the view of the rear of the car. You can see here the TSAC itself. It is in a quite obscure space, only because, as Cooper already talked about, it's going to be dropped down to if we ever need to do it. Motor is in the backside, and inverter is in between the low voltage box and TSAC itself. And now we're going to look at the high voltage subsystem of the car. This is the general schematic for the inside of the TSAC. It's of course not completely finished yet, but we are really close to doing that. This is the schematic for the PCBs that govern the cells within the TSAC. And it looks rather nasty, nice, so I wanted to show it off. Now we are going to talk about some projects that we already finished within this academic year. I have to clarify that those projects are finished in the design phase, not the manufacturing. So manufacturing is yet to come. Starting with T-cell, this is a rather important component of the car, as it's rules mandated. It means attractive system active light, and it's engineered by our engineer Alexia. Here you can see it on the car. It's located on the main hoop. It is basically a circuit that controls a set of LEDs, red and green, that signal to the outside world of the car that the car is either active, or it is in the ignition state, or it is completely turned off and is safe to touch. So yeah, basically a safety thing. Here you can see the physical design of the printed circuit board. It is already iterated upon, so that's not the last version, but you can see some interesting features as low voltage side on the left side and high voltage side on the right. Here's the schematic of the entire thing. Now it may look not that complicated, but actually there's a lot of analog logic, which is quite hard to get right the first time. Moving on to the AVPS, that's a small circuit designed by Jonah. It's located here in the pedal box assembly. Basically, it is a device that ensures the signal integrity from the throttle pedal of the car. Also governs the redundancy within the 2 sensors that are mounted here. You can see on the axle there are 2 sensors. Well, as I said, it's to ensure the redundancy within those sensors so the car doesn't launch itself off into a cliff. Here's this small layout of the schematic, and this is the physical design of the PCBs. Next one is the dashboard. The dashboard is the main point of communication between the electrical systems of the car and the driver. It's mainly software work for us, as physical design is going to come a bit later. What is important to understand is it's not only a display, it's actually a point that aggregates data and telemetry from the entire car. It packages that data and also wirelessly sends to the ground point somewhere, so we can track the telemetry in live. Here's a quick mock-up of how the dashboard might look. Of course, that is a subject to change. Moving on to the next project that is going to be housed within the low voltage box. It's one of the few projects that are going to be there, but within the low voltage box, there's going to be a lot more auxiliary electronics, so it's rather big. It's called BSPD. It stands for Brake System Plausibility Device, which is designed by Jan. The purpose of this circuit is rather similar to the APPS circuit. It basically ensures that the driver there is sufficient pressure within the brake lines of the car. Here's the schematic. If you want to look at it, I can provide it later. There's the physical design, and that's pretty much it for the circuit. Next, I'm going to talk about educational aspect of the team. It's important to understand that not everyone in this team is an actual engineer. Some students have never even touched basic printed circuit boards or the design of those. Most of the projects that I just showed are designed by people who came to HARD and said, I want to learn. And during this academic year, we were trying to provide the necessary training and learning opportunities to all of the people that are a part of HARD team. We also try to communicate between the teams, or between mechanicals and electricals, so so all of the members actually learn something new for them. As I said, for example, Jan and Alexia, they designed quite complex PCBs by their own in a span of around 7 months. And I would say that it's important to understand that we should never be afraid of coming to a new team and just trying to learn something. You should try something and maybe you'll like it. You can build a career in that. Moving on to what's next. After the rollout, there's going to be still a lot of design work. We have multiple projects that we need to finish, such as charger of the car or the R2D circuit that basically is an analog circuit that makes the car, checks everything and makes the car turn into the drive mode on. There's also multiple other circuits that are less important. The important thing is that we cannot run with them, without them. So we have to build those, have to test them, have to manufacture, test again, and then iterate on design as well. It's quite similar to mechanical team. We just have to iterate because it's going to fail and we're gonna need to debug all of that. And there's much more to come because, of course, the manufacturing itself is quite interesting and it's a whole new world of fun and games with every team member of the car. So thank you. Next up is the driverless design.
So hello everyone. Now I will be talking to you about the driverless design of our car and what we have done so far. Firstly, before we even begin, we need to set up the talking between the components. This is all done through the ROS stack. As you can see, this communicates our sensors, our perception, and then everything talks back and forth with the logic inside. As you can see, it's very modular in order to easily find problems and debug them. Next, I would also like to talk about the perception of the car. This will be done through the YOLO algorithm, which is an architecture to perceive cones and their position in the picture, as you can see in the picture shown. It basically allows us to detect cones or any other objects in front of the car or around it. This is combined with other sensors to look at how far the car is and estimate its position in real time. Lastly, we are developing and training our software on the Unreal Engine 5. This allows us to test and debug our software in a safe way compared to actually deploying it in the RC car later on or in the actual car. This allows us to experiment faster and train our models much more reliably than later. And this is what the current roadmap looks like. We are currently developing the simulation and the implementation of the Unreal Engine. tweaking the physics and building the tracks. We are at the same time working with the AI perception and navigation around the track together with the ROS and robotics stack so that everything is able to talk at the same time. Lastly, after we are done with all of this, we are planning to implement everything on an RC car, and then after everything looks good on the RC car, we plan on implementing everything on the actual Formula car. Thank you, everyone. I will now introduce our communications, Shiva.
So that was a lot of engineering in the past few minutes. And let's talk about the other side of the Hanze Racing Division, obviously the communications department. The communications department, we've split roughly into 4 different teams: the marketing team, the graphic design team, the events team, and the acquisitions team. Shout out to the events team for organizing this event pretty well. I think we're all happy with that. The team has considerably grown from what I heard was like, 1% last year. And we've gotten a lot bigger team of 16, which also has a lot of help from the engineering department for when you want to make videos or when the communications people have any technical questions about the car. But yeah, that's us having a nice little meeting outside when it was nice and sunny. And it went up on our Instagram page. So starting off with our marketing department, you can see them spread all around in the front, some over there, some over here in the front. But they obviously make the sponsor posts that you find on our Instagram, LinkedIn. They deal mainly with recruitment and member retention. They make very fun videos. For example, that one marketing video of us with the Beta Business Days bunny. I think some of them are, yeah, there they are, yep. And for all the open days, that's us at one of the open days at the Hanze in ZP11. And of course, we have the fun work blogs and everything that the Instagram team also puts out. The team has done a lot of work. On just the Instagram itself, they've hit 60 plus posts. And when we look at all of our platforms, I think they've easily passed 100 plus posts since the team has formed this year. You can see some of the designs they put and some of the latest videos on that little screenshot over there, where I was asked out to join the rollout today. We do have growth from 1900 to almost 2400. The number has changed a little bit since this presentation has been made. And we've got blogs coming soon. We've gotten a few written up and they will be posted soon. And with the growth in our team, we also have plans for long form videos. The acquisitions team, which in my opinion as the finance manager is the best team. We mainly, of course, deal with sponsor relations. You might have seen some videos, some emails from us. We deal with buying parts and services. We deal with acquiring the knowledge partners, for example, ICD Doctrine, for whenever we have any technical questions. And of course, we did talk with Beta Business Days and other associations when we had to have events with them. Here are some of the events we've done through the help of the events team. You can see, again, once with our bunny, and then a picture of us at an event with Glitch, which was the study association for game design, I believe. And of course, we have us having a little workshop hosted by one of our professors at the Hanze, where we learned how to deal with fiberglass manufacturing. They, of course, do deal with other events, such as this business workshop for DISC that we had with our sponsor, No Milk, today. And we held multiple alumni evenings. We worked with associations like Glitch, Versorium, Lugus, HSV, and of course, our partner, No Milk, today. These are some of the few events we've had. We had even more. And anything that you see, for example, this presentation, the clothes that our team members are wearing, any of our posters, the shirts, of course, have been designed by our graphics design team. They did a pretty good job. I've heard a lot of good reviews from all the art that we've posted. And something experimental that we're trying out this year is streetwear merch, something that doesn't look too formal and something that looks a bit, casual. And of course, we're having our usual official merch, stickers, polos, everything like that. All of this is only possible, of course, with the help of our partners. Our team has done a good job getting more partners this year that help with knowledge partners, parts, services, and all of this. For example, we have the Hanze, Shell, 3D Connection, Exact. When we are very thankful to all of these members for helping us run the department, helping us design the car with their knowledge and all their other resources. We obviously do like to give back to our partners. We provide a pipeline to talent. We've heard that companies are really happy with the talent that they find out through our organization, how they are instilled with skills that you can't really find within the academic walls of our university. And our team manager do say we work in a way that is essentially like a mini company, which is something that most academic circles can't really give you. And so they're pretty happy with that. And of course, we have our social media and marketing team that show off all of our sponsors and all the work we do and everything that they provide for us. For some people, I believe some of you guys are interested in joining the team that are guests. Here's a quick QR code. Yes, okay. And yeah, thank you for your attention. And
So yeah, thank you very much, everyone, for taking some time out of your day for us and for listening. Our engineers have insisted that I need to tell you that if you have any questions, you should ask them. But I do warn you that they may never stop talking once you do. So just outside, in the dining area, we're going to be providing some refreshments, including some pizza and drinks. So do feel free to have some snacks and have some chats with our members and anyone else who is present. And yeah, thank you very much.